All right, welcome back. We're ready to change gears a little bit and move from our lecture series where we were reviewing all of the different ASTM basic categories of AM processes. And now we're going to move towards an overview of design for additive manufacturing. Okay. And hopefully a lot of the things we're going to talk about will be very relevant to your project as well. So the first thing I want to start with is just ask you to think a little bit about design for AM. Right? How would you define it? Right? Think about that for a little bit. Think about what your definition would be. What makes it different from other design processes? So in some design classes, we learn about design for manufacturing in general, maybe design for injection molding, design for machining, right? What makes design for AM different? All these different unique capabilities that it gives us, this ability to do complex geometry, that has to be part of our design definition, doesn't it? So if we just copy a standard part, right? Think about the pen that's probably in your hand as an example, right? Most likely if it's plastic, it was injection molded. If you just copy that in AM, is that an example of design for AM? What if you make changes to it? What if you have to change some of its dimensions or material properties just a little bit? Does that count as design for AM? Is that different from maybe completely designing a pen from scratch? Making something that's really cool and aesthetic and intricate and looks almost like, I don't know, bone tissue or tree branches or something like that, really takes advantage of AM. Is that more design for AM? Let's think about that a little bit. All right, so let's think, when we think about design for AM, the reason that question that I asked you is a little bit difficult is because there's a lot of different types of design for AM and a lot of different design projects and problems that we can approach, right? So let's think about that for a little bit. If we think about design for AM, we can really think about it as something that's on a continuum, right? I'm going to draw this continuum here for us. Okay. Now over here, what I'm going to do is I'm going to write over here, I'm going to write restrictive, DFAM. Okay. And here I'm going to write opportunistic, DFAM. And DFAM here, of course, means design for additive manufacturing, right? DFAM. So I don't have to keep writing that out. Now, restrictive DFAM, right, is different from opportunistic DFAM. If we think about those words, we can probably think a little bit about why those two might be different or how they might be different. So restrictive DFAM basically tells you what you can't do, right? So for example, in polymer powder bed fusion, you really can't build features less than, somewhere around maybe 0.4 millimeters in thickness. They just disappear after that. You have to have certain clearances between moving parts, otherwise they'll fuse together. You can't build a hollow, solid, watertight sphere. Otherwise, you can't get the powder out. It won't be hollow, actually. You have to have a way to get the powder out. Those are restrictive DFAM. They're basically telling you what you can't do or the limits of what you can do. Opportunistic DFAM, on the other hand, is saying, oh, you've got additive? That's cool. So let's figure out how to do a part that's customized, or let's think about putting a lattice structure in there because we can. Or use multiple materials where one material is hard and the other one's a little bit more flexible, and using them in strategic locations so that you get almost a flexible part or something that's both strong but durable. All right. So if we think about this as a continuum, then there are a number of ways we could design parts and eventually additive manufacture them. So on this end, what we would start with would be conventional parts, right? Replicated with AM, okay? And if that's where we start over here on this restrictive end, we start here, what that means is we start with an existing part, or conventional manufacturing, Okay. So this is a part that we would have typically made by molding or machining. And then in terms of design, we really do very little to change the part. We might do some selection of orientation, selection of process, a selection of material. And then we might do some very minimal, say, size or shape changes. Okay. The outcome in this case would be a copy of the original design. We've got something we've made in another way. We want to make a copy of it, maybe a replacement part, and we want it to be as close as possible to that original one. Then if we look at the other end of the spectrum, we have parts designed exclusively for AM. All right. So we start in this case with functional requirements. What does the part need to do? Does it need to be lightweight, less than a certain mass? Does it need to withstand particular structural loads? In which case it may need to be strong, particularly in certain locations. Are these loadings going to be dynamic? So do we need to worry about fatigue? All those types of things come into place. Does it need to mate with another part? In which case, at that mating surface, do we have tolerances that we need to keep? And all those things are really important. And so if we start there, then our design process then becomes very open-ended. So we basically got complete synthesis for AM, right? And we might end up with a part that looks very different from anything we've seen before. And the outcome is going to be a design, right, tailored for AM to really take advantage of additive manufacturing's strengths and unique capabilities. And in the middle, we can have something in between. So parts, for example, adapted for AM, right? And here you start with the same thing you start with conventional parts. You start with an existing part for conventional manufacturing. And then in terms of design, you adapt the geometry, right? So you might, for example, consolidate a couple of components in the original design because it makes sense, right? Then in additive, you can make that more complex structure and it minimizes, say, assembly costs. And the outcome will be a design adapted for AM. Okay. All right. So, what is our definition, right, of DFAM? Well, it really depends. It could be, if it's very restrictive, the definition could be making sure that a part can be manufactured using AM and making small design changes to it. And then overall, on the right-hand side of this, DFAM could be, synthesizing a part that leverages the unique capabilities of AM. And I really like that. I really like that broader definition of design for AM. Right? And that, to me, what we're trying to do is enhance product value, right, by synthesizing a part to leverage and respect. So I'm going to put that little restrictive clause in there, the unique capabilities of AM. Okay, so that leverage there is very opportunistic, and the respect the capabilities of AM, is a little bit restrictive. All right, so let's, now that we've got some of that basic terminology down, I give you a little bit of an example here of what I mean by restrictive and opportunistic DFAM. right? And here, if we look at restrictive DFAM, we're really talking about, in this case, rules and guidelines. What can you do? What can't you do? So in this case, you can see we've got a test part here with fonts of different sizes and raised to different levels, dimensions above the plane here. And over here on the left-hand side, we've got some different charts. One is for embedded lettering and another one is for raised lettering. And these charts tell us a little bit about what we can and can't build. So the rows here are fonts. And the different columns here are to what extent we've either embedded or raised the font. And the green tells us we can build it, the red tells us we cannot. We're going to look at a bunch of these types of design guidelines later on, but the bottom line from this one would be if you want to do parts with raised lettering, then you want to make sure your fonts are large, say 16 or 18 point. Otherwise, you could get, failed builds, something like this, where you can't really read the letters at all. And so that's an example of restrictive DFAM. We have some lettering that exists on the part. We need to recreate it. What can we build? What can't we build, right? How can we redimension it so it'll build? On the right-hand side, you see more of the opportunistic DFAM, this idea that you could use AM to enhance the functionality of a part. So look at this example here on the bottom, right? And that example is a cast for a broken limb or for a broken bone somewhere in the arm. And one of the cool things about this cast is you can see they've made use of AM instead of making it a fully solid cast. They've used cellular structures in there. It looks a lot like something you might see in nature. To me, it almost looks like cells in a leaf. And you can also see that they've taken those cells and they're big in some areas where you don't need a lot of support, and then they're small in others. Maybe this might be a broken wrist to restrict movement there. So that's opportunistic DFAM. Let's completely rethink the idea of a cast and make it more suited for what we want to do in AM. All right, so we talked about replicate, adapt, design originally for AM. So here are some examples to help us think through what the implications of those things are. So if we replicate with AM, here's an example. This is an example of a link and bracket assembly to help secure engines onto an Osprey helicopter. And so you can see these parts down here. This is what it looks like after it's been finished. This is what it looks like when it comes off the build platform before it's finished. And then over here, you can see what it looks like as part of the build. You can see the part inside. You can also see quite a few tensile bars that have been built so that they can characterize the material properties alongside it. So this is an example of replicate with AM. And the reason it's an example of that is that we're starting with an existing part, this linkage and bracket assembly, and we're just trying to replicate it with AM. We're not really trying to change it. In fact, we want it to be as close as possible to the original part because we're going to stick it on this Osprey helicopter as a replacement part. So primarily here, we're going to use restrictive tools, guidelines, tolerances, things like that. What can we build? What can't we build? There's an internal hole inside of this linkage here. Most likely what we'll do is we'll build it broad. We'll build the hole too small and then we'll machine it out later so we can keep the tolerances on that. Why would you do something like this? Well, sometimes you do it because it's faster than setting up a new tooling process or a new casting process or sending it out to be casted. Another reason we might do it is to fab on demand, so we can keep these digital files on hand and then fabricate them whenever we need to. You can also do that kind of with CNC machining as well. But in this case, what you want to do is to try to prove the technology. So in this case, they have a part, they build it, they use it, they've characterized the part really well. Now they want to see if they can recreate it on additive technology. So that could be another reason to try to replicate. But often it's because you want to have a part quickly and to be able to fab it on demand whenever you need it without holding it in inventory. All right, so then let's look at adapt for AM, right, which is our second category. Here we start with an existing part and modify it to take better advantage of AM, right? So our existing part is on the left-hand side. This is an example down here of ductwork for a Boeing aircraft. And on the left-hand side, you'll see that the original ductwork had a number of parts, 16 parts and fasteners to be precise. When we fabricate it with AM using selective laser sintering, we reduce it all down to one part. Now, in this case, instead of just making the parts as they were, it makes a whole lot of sense to modify the geometry so we get better bang for the buck from our AM process. So there's a number of things that have been done here. So you take multiple parts, like the top and bottom half, you combine them, you eliminate the need for fasteners, you eliminate the mating surfaces, and you build it all as a solid part. You can round off some of your edges as needed to make it easier to build in additive manufacturing. You might change some parts of the inner geometry. You can combine multiple parts and have this complex part. You reduce the need, you don't have any small holes or mating features or fasteners or anything by combining all these parts. So you've made some pretty substantial changes to the geometry, and so that is why we call it ADAPT for AM. All right. So you might use some restrictive DFAM guidelines, such as, for example, how thick does the center beam need to be, or the center fin need to be in order to resolve properly. But you also might use some opportunistic design for additive, in this case, consolidating multiple parts into one. Some of the benefits of doing this speed, right? Your assembly time is certainly going to go down. You have fewer errors in the assembly. You don't have any problems with mating parts or assembling things incorrectly, having a fastener come loose. Lower cost by having it in one part, reducing your assembly time. You can fab it on demand directly from inventory. And in some cases, you can have enhanced functionality by building it this way, right? Some parts you'll see them adding cooling channels or other things like that that you wouldn't otherwise be able to do. All right, so the third example category was design or optimized specifically for AM. This is an example down in the bottom of an oil and gas component that we're working on. And here you can see in most oil and gas components, you've typically got fluid channels that you're trying to snake around maybe some electronics or other things and get all those fluids into or out of maybe a cutting area, for example, if it's a downhole drilling tool. In this example, in order to build this tool with all these channels, you'd have to add a lot of support structure inside. But in this case, instead of adding support structure, what they've done instead is to lightweight the inside of the part with a lattice structure. And so the lattice structure eliminates the need for support structures, right? Because this is being built in metal, and you have all these snake-like channels that are running through it. And it also adds some lightweight stiffness and strength to the part. So it really does double duty. And so this is an example of a part where they've basically started with opportunistic DFAM. How can we lightweight it, make it strong, stiff, complex geometries? And the potential benefits could include enhanced multifunctionality. So this part's actually lighter weight than it would be if you designed it conventionally. You can also get some speed and cost advantages. Maybe you use less material in this case, especially if it's an expensive alloy. All right. So some of the benefits that you'll see companies cite, in this case, it's an aerospace company, Boeing. We'll talk about from the design perspective, you can get enhanced flexibility in your design process. You can also do direct design from a 3D model to direct model to manufacturing. So you take a 3D model and directly manufacture it. In terms of production, you can eliminate tooling costs, right? By going to additive, you can have faster part delivery times in many cases, especially if it's a polymer process rather than a metal one. You can have flexibility in your suppliers. You've got the digital file, you know how to build it. As long as they have an additive manufacturing machine that matches, you can build it. You can get sometimes a pretty big cost reduction and cycle time reduction by building these parts. You can reduce the amount of material, and so on and so forth, especially if that material is expensive like titanium. All right, you can also lower your inventory costs and your transportation costs by building it on demand near where it's needed. Okay, so let's talk a little bit about opportunistic AM, right? So restrictive AM, design for AM, we're going to cover in detail in some subsequent lectures. So in this lecture, I want to dive a little bit more into opportunistic DFAM. So what are some of the different ways that we can take advantage of AM? What have we seen? So here are some examples that are listed on this slide. One could be complex geometry. And that complex geometry here could be broken down into a number of different types of complexity. The shape could be really complex. There could be hierarchical complexity in terms of lattice structures and other things that take advantage of additive on multiple scales. There could be functional complexity, so you build devices, functional devices in a single build, maybe an entire assembly or a moving parts built together. You could also have material complexity where you build multiple materials. We saw the capability of doing that in Objet. We also saw that in Lens. We can also have customized geometry in parts. If we go back up to here, customized geometry in parts. So we can customize it to a body. We can customize it to on demand. Consolidate parts together, integrate multiple parts into one, reduce assembly time, assembly costs, inventory, etc. And then we can just give ourselves more manufacturing freedom and not have to abide by and respect all of the really restrictive rules that we see in, say, injection molding, casting, etc. So let's take a look at some examples of some of these. So here are some examples of complex geometries. Some of them are aesthetic, right? So you can see up here what looks almost like a feather. Here it looks like some sort of a tire, which you could say might be aesthetically pleasing, might not be aesthetically pleasing, depending on your taste. I find it a bit ugly myself, but you might disagree. We also have here, in this case, the ability to take complex geometry and lattice structures. So the wings of this UAV, in this case, are built from lattice structures. So that makes them very lightweight, but still very stiff and strong. We can also see, the ability to, say, use biomimicry. You can see that really coming into play here inside this structure where they've got a really complex cellular structure inside that looks very much like the insides of bone. Again, maybe for lightweight strength, maybe cooling, other things like that. All right, so custom geometries, right? Think about that. And let's look at some examples of that. So one example here, up at the top, you'll see our cranial implants. So these have been done for a number of years at Walter Reed Army Medical Center near DC. And there what they'll do is if a soldier comes back and their skull has been damaged, let's say by an IED, an explosive device, what they'll do is they'll take a CT or MRI scan of the damaged skull, and they'll be able to build an implant that specifically replaces that's customized to that shape. Oftentimes those implants are porous, so they relieve pressure from the surgery, and then the bone surrounding it can grow into that implant much better. You also see here in the bottom some examples of using a CT scan of an ear canal and building a hearing aid that matches that precisely. So presumably it would be more comfortable and would fit a little bit better. And then here we've got this example we've talked about before in class of these Invisalign technologies. And in this case, this is a stereolithography machine. You can see these parts have been built on a build platform. And these are mold. You'll take stereolithography, you'll build molds for braces, and then mold the braces around that mold. And in this case, each pair of braces is designed specifically for an individual's tooth pattern. And then every few weeks, you'll get a new set of braces that gradually move your teeth back into shape. So a really good example of custom geometry that would be really expensive and time-consuming to make in any other way. Here's an example of hierarchical shape complexity. So we've talked a lot about lattice structures. Often it's for lightweight, maybe stiffness and strength. But in this case, it's not only for stiffness and strength, but it's also for bone ingrowth. So this is an example here of a hip implant. And typically what you'll find is it's a ball and socket joint, right? So this part down on the bottom has this really complex cellular structure. And what that does is it allows the bone to grow into that porous structure and adhere to it well. It also helps distribute the loads across the bone and avoid stress concentrations that tend to weaken and sometimes fracture the bone, and increase the likelihood of success for a successful surgery, sorry. And so this lattice structure part would then go into the hip, And then this bottom part here, this ball of the ball and socket joint would then be attached to the leg bone. Okay. Here's another example of custom geometry. This is dental work, taking scans of a patient, converting them into CAD models, and then from there building crowns. And so here you can see a wide variety of crowns with their support structures still attached in an EOS Metals machine being built. Here's an example of part consolidation. So in this case, what we've got are ductwork again for an aircraft. And on the left-hand side here, you can see a wide variety of components with straps and multiple fasteners and things like that, holding them all together. And then on the right, you can see that completely consolidated into a single piece duct. And you can see some fabricated versions of those here in the bottom. This would have been built in polymer powder bed fusion selective laser sintering with an aerospace grade nylon. Here's another example of part consolidation. Some of you may have seen this. This is the GE LEAP engine. In this case, they consolidated a number of parts down into one part. They used some complex flow patterns to be able to get better performance, better injection with this fuel nozzle. They've also, by eliminating components, they've eliminated lots of brazes and welds, and that in turn helps with durability to make the parts last a little bit longer. Here's an example of complex geometry, right? So this is an automobile component. It has cooling channels. You can see it on the left here. You can see the cooling channels in yellow. Those cooling channels are machined and drilled into the piece. And then on the right-hand side here, you can see that some of those cooling channels now have become, with additive, have become more conformal. We're able to redesign the part, cool it a lot better, and then also trim some material off in several locations so the part's a little bit lighter weight. Here are some really cool multi-material aspects and functional aspects of complexity. So we've talked about how Lens, for example, can fabricate in multiple materials, and this would be a really good example of that. So this is a tool where we've got copper that's embedded, presumably for conductivity. And then we've also got an Invar core, and you ask yourself, well, why would you use Invar? Well, it turns out Invar is used for applications where you want a really low coefficient of thermal expansion. So as something heats up, it maintains its original dimensions quite well. You'll often find Invar used in like supersonic applications sometimes as aircraft move really, really fast and break the sound barrier, their skin starts to heat up. And if it all expands, then it becomes difficult to hold the joints together. But if you use Invar with a low coefficient of thermal expansion, you don't have such trouble with that. We've also talked about how the object can use multiple materials. And here's an example here of just an assembly built with multiple colors. And then over here, we've got a functioning wheel assembly. So we've got a rubber-like tire that can help dampen some of the shocks and the loads. And then we've got a rigid hubs in the center of the wheel, right? A rigid frame for the wheel. Here's an example of printed electronics. So this is multi-material and multi-functionality in terms of complexity. On the right here, you see a part from Voxel 8. This is a startup that was spun out of some work done at Harvard. In this case, it's a reasonably simple process. They do material extrusion for the plastic that you see here that's in orange. They'll stop periodically and they'll use a direct write. They'll write down conductive inks to connect different parts together, like a battery in the center to the motors here on the outer edges. And then they'll also place things like motors and batteries inside when they need to be placed there. On the left, you'll see some really cool printed 2D and 3D electronics from the University of Texas at El Paso. In this case, let's take a look at the next slide and we'll see a little bit about how they're made. So you start out with your typical CAD file, create an STL, import it into in this case, this is a 3D system stereolithography machine, build the part out of stereolithography, and then what you can do is you can pick and place electrical components, microprocessors, things like that. And then finally, you use a process called direct write, in which the name is fairly descriptive of what it is. You basically take a nozzle that's a lot like a pen and you write down conductive inks and you use that to connect the different microprocessors together. And then finally, here's my last example it's called 4D printing. So what's 4D printing? Well, 4D printing is a name for printing three-dimensional parts that change in a fourth dimension, which is time. They change over time. Usually there's some sort of multiple material aspect that's used to make this change take place. In this case, these parts are actually built on an object printer, and they use something called a shape memory polymer that recovers its shape when it's exposed to a stimulus like temperature or light. So you might, for example, build it in an original, say, flat configuration, and then bend it, expose it to temperature, and then have it assume a different shape. So here you can see that as that part is heated up, it starts to fold and bend into a different box-like configuration. And you can take a look at the video if you'd like to see that happen in real time. So basically, as it's exposed to temperature, it changes its shape or configuration. All right. So how do I implement opportunistic design for AM? All right. So that's a lot of stuff that we just covered, a lot of really complex design problems. So my suggestion as a starting point is that there are a number of design for AM heuristics that are available for you to take a look at. And so I've uploaded to Canvas a couple of examples of really good heuristics. One is from Singapore University of Technology and Design, another is from ETH Zurich. And what both of these groups have done is they've created sort of ideation cards, if you will, that stimulate you to think about some of the different things that additive manufacturing enables. And so the way to do those is as you generate ideas, I suggest, sketching ideas for your problem individually or as a group. And then trying to see what you can, looking at each of the heuristics, seeing if you can incorporate them into your design. And then when you're done reviewing your designs as a team to see what everybody's come up with, consolidate some of your good ideas into leading designs and iterate as needed. So let's take a little look at what some of these heuristics might look like. So here's an example of the heuristics from the Singapore University of Technology and Design, right? And so this is an example of a heuristic. This is a heuristic card. And here what you can see is that it starts out with a little description of the heuristic. And so this one happens to be leverage structure for function. So find a way to achieve your desired mechanical properties by tailoring the geometry of the structure itself. And so down here you can see a simple before and after. So in traditional manufacturing, if you wanted a spring-like mechanism, you'd probably assemble a mass with a spring. But in our new additive technique, we may be able to take that mass itself, let's say it's a beam, and design it in such a way and build it in such a way that it itself is a spring. So here's a couple of examples then on the right. The first one is a doorknob latch. So as you twist the latch, the whole assembly starts to deform, and it'll pull a latch and it'll unlatch a door latch. Then on the bottom here, you can see it's basically a set of pliers. As you squeeze on one end of the pliers, it will grip the other end. And it's all made in one piece, right? And they've used structure in that case to try to get that compliant mechanism type of motion. There are a number of different principles, and they're of different types. So some of them are, like in blue, are product principles that help you design parts and products. Some of the red are process principles that help you look at ways to basically change the design, the process of making things. Then orange is the process of design, so how you might change the process of design. And then this teal or green color is printing. So how might you change the printing process or guide the printing process to make it more successful? These are mostly aimed at FDM. The green ones are, but other principles are widely applicable. All right. So you can kind of leaf through some of these and see examples of some of them. Here's another one for design, leveraging cellular structures. We already saw one about changing the structure to change the function. This is leveraging cellular structures as a way to reduce weight, or cost, or preserve stability. And so you replace a volume with cellular structures. Here you can see in the upper right a fuselage for a UAV that has been replaced completely with cellular structures. And then on the bottom right here, we see a helmet insert that uses cellular structures to absorb energy, things like that. Here we can see another principle card where it asks you to look at your joints and interfaces and try to eliminate assembly steps in time. So you might be able to print functional joints or interfaces directly, or maybe just consolidate those interfaces. So here you can see in the bottom left a hinge that's designed to be printed as a single part compared to the multiple parts that are on the left. It looks like it might have been printed here with objects, so different colors, and you can see what's going on. Here on the right, you can see you've got a dress that needs to be able to flow and be flexible. And the way that's done is taking completely rigid materials, but looking at their joints. And you can kind of see that a little bit here in this bottom right-hand corner, where individual triangles are connected to each other using these rotational hinges so the dress can move freely and be flexible like a typical dress. All right. So how do you use these again? Right now you have some examples of what I mean by these heuristics. As you're sketching out ideas to solve your design problem, you can use this in your project. Think about these heuristics, go through those. Those are kind of meant to be used as cards to kind of stimulate good ideas. Go through those heuristics. How could I apply that to my design? How could I apply this one to my design? How could I apply the next heuristic to my design? Keep sketching different ideas that apply those principles to your design. All right, so what I'd like you to do now is to take a little pause, and I want you to think about, let's take an example. Let's take a bicycle frame, for example, just a standard bicycle. Imagine we're going to additively manufacture the frame of that bicycle. What would it look like? Let's go back and look at some of these heuristics, right? And see if we can apply them to the bicycle frame. How would it look different if we did that? Okay. All right, so take a pause your video, sketch a few ideas, look at a few of those heuristics, and then come back and we'll talk about it. All right, so I'm going to assume that you've done that, and I'm going to come back and I'm going to show you a little bit of what I did in the meantime, right, for the bicycle problem. So what I did first of all is I sketched out the sort of a bicycle frame. You've got a seat, you've got handlebars, you've got wheels, of course. And I looked at a few of the heuristics, right? One was about functional integration. And I thought, well, or basically integrating parts. We've seen some heuristics about trying to integrate multiple parts into one. And I thought, well, one easy thing that you can do here is just to fab in one piece, to integrate functions into a single part, no welds, right? We don't have to do any welds. And so that would certainly reduce assembly time for a bicycle. That's one thing we could do. The second thing I thought about there is the heuristic that we just saw from the SUTD group on using cellular structures for lightweighting. And I said, well, you could take one of these beams, for example, here, and you could lightweight it by, instead of having a solid part, it could look a little bit more like bone or a spider web, right? In fact, we might even be able to think about completely redesigning the structure of the bicycle, right? And we've basically just got a seat, some handlebars here, and we've got wheels and a place here where we need to pedal, right? These are our pedals, and then we've got two wheels here. And everything else, we basically have to support load here, we have to support load here, and we have to support load here and here, and we have to be able to pedal here. Everything else is up for grabs, right? Maybe it becomes a really cool topology optimized structure, right? That is very sparse, right? That has something like this that you build in the machine, and uses maybe a little bit less material if we do this right, and requires no assembly, no welding, right? Maybe there's something like that that we can do. Also thought about customization. So we talked a little bit about customization, changing the geometry for each individual user. Is there a way we can do that? And that's mentioned in some of the heuristics. And so one of the things I thought about there was perhaps changing the geometry for a custom ride, right? So I tried to put in a set of additively manufactured leaf springs sort of here. So taking that post that you sit on and replacing it with something like that. You can maybe change these leaf springs, the geometry of them, to give a harder or softer ride depending on the preference of the individual. That might be something you could do that would be really cool. And I bet you thought of a lot of other things as well, right? And so what I want you to think about as you're doing your project is how can I, incorporate some of these ideas? What opportunistic DFAM things can I incorporate into my design? How can I really make use of additive manufacturing? All right. So the other thing one of the things I'd like you to do, and I'll send an email out as well, is to think about, again, how would some of these heuristics influence your design project? So go back and look at the two that I've uploaded from SUTD and from ETH Zurich, and go through those heuristics and see which ones might apply to your project. Sketch out some ideas for me. And then bring them into office hours at some point in the next week or so and show me some of your ideas. And if you do, I'll offer you a couple of points of extra credit on your midterm exam as well. So if you can come in and show me some of those ideas in office hours. All right, that's it for April 2nd. And I'll see you in office hours. And next week, we will continue with our Design for Additive Manufacturing lectures.